Chapter 12 Helicopter Emergencies Introduction Learning emergency procedures is an important component of helicopter flight training. The instructor must ensure a student is completely familiar with the emergency procedures section of the Rotorcraft Flight Manual, RFM, pertinent to the helicopter model being flown. Many instructors require students to memorize emergency procedures and are satisfied when the student offers a simple recitation of the steps outlined in a procedure. While memorizing steps in a procedure is an important element of acquiring knowledge, it does not supply the knowledge needed to solve a problem or provide a solution to something that is not covered by the newly acquired knowledge. As discussed in the Aviation Instructor's Handbook, understanding, or the ability to notice similarities and make associations between the facts and procedural steps learned, is an important next stage in the knowledge acquisition process. Once the student has mastered the emergency procedure, an instructor can enhance this level of learning by creating a scenario that leads to a malfunction the student must resolve using emergency procedures. Proper scenario-based training requires research by the instructor to make this meaningful to the student. Take time to research an accident that replicates the training being performed. The National Transportation Safety Board, NTSB, website, www.ntsb.gov, provides several links that may be helpful. Once research has been completed, sit down with the student and discuss what factors may have caused the accident. By discussing the causes of the accident, a thorough review and check of the student's depth of understanding can occur. As an example, there are many possible causes to an engine failure. Internal engine failure, fuel starvation, contaminated fuel, drivetrain failure, air inlet interruption, or hardware failure are just some of the possible causes. Discuss in detail the cockpit indications that the pilot would have seen. What instrumentation differences may have been observed? What is the aerodynamic profile as it applies to this situation? What actions by the pilot were necessary and were they correctly assessed and taken? Follow the discussion with a training flight that allows the student to view the gauges, indications, and flight profile that permit the student to practically apply the lessons learned from the scenario-based discussion. This type of training requires the student to exhibit knowledge of aircraft systems, as well as higher-order thinking skills, HOTS. The outcome of any emergency that might occur in an aircraft is directly related to the pilot's ability to react instantly and correctly, since there may be limited time to analyze the problem. Although a pilot could spend an entire career in helicopters without actually encountering an emergency situation, the demonstrated ability to cope with any situation is essential to safe operations and pilot confidence. Therefore, it is necessary to introduce emergency procedures early in the training programs and to practice them frequently. Autorotative descents. An autorotative descent is a part of numerous emergency procedures in helicopters. Autorotations should be introduced first with an intentional entry so the student can practice establishing an autorotative glide. When the student develops proficiency in performing autorotations to a selected spot, the instructor should initiate autorotations when the student is not expecting them by announcing engine failure. Figure 12.1. As the student's ability to do an autorotation progresses, the instructor can use scenarios like decreasing oil pressure or zero oil pressure to stage an engine failure scenario. This will better prepare the student for an actual engine failure as there are usually prior indications that occur and need to be recognized. A student who becomes accustomed to someone announcing engine failure may never learn what the prior indications of the actual failure are. Refer the student to the Helicopter Flying Handbook and use it as a guide for a detailed discussion of the techniques for performing autorotative descents. Straight and autorotation, with instructional points. As the student demonstrates the ability to react properly, the instructor should announce engine failure as he or she retards the throttle to further develop the student's reactions. Never give the student a simulated engine failure unless an autorotation can be made safely to the surface. Do not assume a power recovery will prevent a landing to an unsuitable area because the engine may hesitate or even completely shut down when rolling off the throttle during the autorotation entry. To prevent an inadvertent engine shutdown during practice autorotations, follow the procedures outlined in the RFM. Perform practice autorotations to a known area free of obstructions, where a safe landing to the surface can be made at any time. Figure 12.2. Demonstrate the maneuver using the manufacturer's recommended airspeeds for autorotative descent over the best gliding speed. The instructor should require the student to review the performance charts and know the minimum and maximum glide airspeeds for the day's conditions. Especially during the early phases of training, the flights should be conducted at higher altitudes to give the new student more time to understand the different descent angles available, using minimum rate of descent airspeeds and maximum glide airspeeds. Some helicopter RFMs also advise of different rotor RPM values for gliding descents. In those cases, Substantial care should be exercised to maintain the proper rotor RPM for the glide and then restoring the proper RPM value for the landing in a safe manner, even if performing a power recovery. Emphasize coordinating the collective movement with proper anti-torque pedal for trim to prevent nose tuck. Nose tuck mainly occurs to certain helicopters, usually those with canted tail surfaces. Nose tuck is the rapid nose-down pitching resulting from a yawing motion causing excessive lift in a stabilizer. This only occurs when the stabilizer is canted upward from the horizontal. Instruct the student to apply cyclic control to maintain proper airspeed. After entering the maneuver, have the student verify and call out needle split, rotor revolutions per minute, RPM, in the green arc, helicopter in trim, and airspeed. During the descent, instruct the student to adjust collective pitch control as necessary to maintain rotor RPM. Emphasize avoiding large collective pitch increases because they result in a rapid decay of rotor RPM. Demonstrate how aft cyclic movements cause a temporary increase in rotor RPM. At approximately 40 to 100 feet above the surface, or at the altitude recommended by the manufacturer, demonstrate the deceleration with aft cyclic control. Explain how the deceleration is used to both reduce forward airspeed and decrease the rate of descent. Point out that the cyclic control is not moved rearward so abruptly as to cause the helicopter to climb. Show how the helicopter is placed in the landing attitude at approximately 8 to 15 feet, or the altitude recommended by the manufacturer. Explain that extreme caution should be used to avoid an excessive nose-high and tail-low attitude below 10 feet. Demonstrate the application of collective pitch as necessary to slow the descent and cushion the landing. Explain that additional anti-torque pedal is required to maintain heading as collective pitch is raised due to the reduction in rotor RPM and the resulting reduced effect of the tail rotor. Emphasize touching down in a level flight attitude. Note, a power recovery can be made during training in lieu of a full touchdown landing. Refer to the section on power recoveries for the correct technique. After touchdown, and after the helicopter has come to a complete stop, lower the collective pitch to the full down position. Discuss the hazards of using the cyclic or collective to slow the helicopter's ground run. Note, numerous tail boom strikes have occurred due to improper collective pitch response upon ground contact and completion of the maneuver. Particular attention must be emphasized as to the proper rate and timing of lowering collective to avoid potential damage to aircraft components. Emphasize the minimum requirements for rotor RPM, airspeed, and trim conditions throughout the maneuver. If the instructor or the student feels uncomfortable with the auto rotation, do not hesitate to initiate a go-around. The instructor is responsible and should terminate the maneuver anytime the parameters vary from normal, or if either pilot determines something is not right. These are common comments that are submitted on accident or incident reports. Therefore, the instructor should be especially aware of these occurrences and err on the side of caution by making power recoveries or go-arounds if any doubts exist. The instructor's primary duty is to ensure the student has safe flights and does not get into trouble. The instructor should highlight the student's understanding of the wind's effects as related to airspeed versus ground speed, and the amount of flare necessary to slow for the landing. The instructor should help the student to cope with the increased airflow through the rotor system in the flare and how to control RPM, both increasing and decreasing. The importance of landing gear alignment cannot be overemphasized during actually touchdowns. If the helicopter is kept in trim, the rate of descent will be the minimum rate. Out of trim conditions increase the rates of descent considerably. Usually, it is useful to demonstrate how much out of trim conditions can increase the rate of descent. Although not usually needed or desired, a steeper descent angle to enable an emergency landing in a very close-in landing area could be useful, but only if the student is trained how to recover and arrest that increased rate of descent. Auto rotations with turns. With instructional points, when auto rotations are first introduced, they are usually conducted straight ahead and into the wind. Discuss with the student that a turn, or a series of turns, may be necessary during an auto rotation to land into the wind or avoid obstacles. Emphasize that the turn should be completed as soon as possible during the descent so that the remainder of the auto rotation is the same as a straight-in auto rotation. Ensure the student is aware that, during the turn, the rotor RPM must be closely monitored as it has a tendency to build during the turn. Airspeed, on the other hand, may be unreliable until the turn is completed. The importance of maintaining the helicopter in trim cannot be overemphasized. Instruct the student to adjust the collective as necessary in the turn to maintain the rotor RPM in the green arc. If the collective pitch was increased to control the RPM, it may need to be lowered on rollout to prevent a decay in RPM. During training, the turn should be completed and the helicopter in position to land in the intended touchdown area prior to passing through 100 feet above ground level, AGL. Initiate an immediate power recovery if the helicopter is not aligned with the touchdown point or if the rotor RPM and/or airspeed are not within proper limits. Power recovery from practice autorotation. With instructional points from an instructor's point of view, it must be remembered that a power recovery, if applied too late or too rapidly, can result in hard landings that sever tail rotor drives, resulting from loss of yaw control, overboosting of turbocharged engines, overtemping and/or overtorques of turbine engines. To avoid this from occurring, think through power application using an early, smooth, and measured response. Do not wait until the helicopter is on the verge of being unrecoverable to initiate the power recovery. Upon initial training, explain to the student that a power recovery is used to terminate practice autorotations or simulated engine failures at a point prior to actual touchdown. The power recovery itself is not an emergency procedure. In the event of an emergency that requires autorotation, the student must be prepared to complete the autoration to touchdown. Emphasize the importance of the throttle detent to avoid inadvertent shutdown. This may occur by unintentionally closing the throttle to the off position. As the instructor, it is your responsibility to verify the power control detent is in the proper position when manipulating the throttle in flight. Additionally, stress the need to increase throttle and join the engine and rotor tachometer needles with the collective in the down position. The power or throttle should be increased to engage the clutch or have the rotor and engine together at about 100 feet AGL. If the throttle is increased too much or too fast, an engine overspeed can occur. If the throttle is increased too little or too slowly in proportion to the increase in collective pitch, a loss of rotor RPM results. Coordinate upward collective pitch control with an increase in the throttle to join the needles at operating RPM. Ensure the student understands the increase of throttle and collective pitch must be accomplished properly. If a power recovery is to be made, slowly increase the engine RPM during the descent to avoid the rapid application of throttle for the recovery. If the student is at all apprehensive about autorotations, be prepared for him or her to either over-control or freeze on the controls. One technique of teaching autorotations is to use power on glides that replicate the autorotational profile, terminating to a hover or with a slight ground run, if permissible. By using this technique, a new instructor can get the feel for the power required and subsequent yaw that occurs during the flare and landing. An instructor should never let the student exceed aircraft limits or the instructor's ability to recover the helicopter. As a teaching technique in many helicopters, a minimum of power can be used for the landing to offer a preview of a full autorotative touchdown. Basically, this offers more cushion and allows a quicker but very controlled touchdown. Having the engine engaged prior to the flare allows the engine to accelerate throughout the flare to produce hover power. The instructor should remember the power recovery is actually a very precise maneuver, requiring the most control movement of almost any maneuver in very little time, and the student is required to transition from power off flight to almost maximum power in a hover. Because so much is happening so quickly, anything the instructor can do to allow more time for the student to perceive all of the actions that must occur in that brief time period gives large returns for the training. Power failure in a hover. With instructional points, whether instructing or evaluating, performing a power failure at a hover is another high accident rate maneuver. The following are some of the common mistakes made by instructors. The first is site selection. Ensure the surface area is a flat, smooth, and hard surface. Students initially tend to have a difficult time accounting for translating tendency. This, in turn, most often causes lateral drift. If conducting this maneuver on a sloping surface, one or more of several phenomena may occur, from dynamic rollover to damaged skid gear. The same can be said for soft or uneven surfaces, as the skid gear may stick, causing a pivot point. Selecting the proper entry height is also imperative. Often, initiating this maneuver from higher than the prescribed entry altitude may cause the student to prematurely apply collective to arrest the rate of descent for landing, leaving the aircraft at little or no available RPM while not yet on the ground. At higher entry heights, a tendency is to attempt to lower the collective to build available inertia or keep the rotor RPM up. Loss of power at a hover with the normal high power setting always results in a rapid rotor RPM decay. Review of the HV chart almost always indicates that there is insufficient power to allow a safe, uneventful landing if the hover height is too high. However the student does it, if the hover height is too high, a hard landing results from a power or driveline failure. There simply is not enough potential energy in the rotor system alone to cushion the landing. This should not be shown to students as it requires a great amount of experience and special training to accomplish successfully. Ensure the student understands a power failure can occur at any time. Hovering autorotations are practiced to develop the automatic response and coordination required to maintain heading and cushion the landing following an engine failure at a hover. Explain to the student that power failures at a hover may occur during either of the two modes of flight, hovering flight in ground effect, IGE, and hovering flight out of ground effect, OGE. Refer to the RFM to generate discussion of the procedures to be used for each instance. Stress to the student that for power failures at a hover while EGA, the collective is not lowered, but held in place until approximately 1 foot AGL when collective pitch is increased to cushion the landing. Explain that when hovering OGA, operations usually fall in the hash-marked area of the height-velocity diagram, which may require lowering the collective and adding forward cyclic in attempt to land the helicopter. As previously mentioned, emphasize the importance of minimizing sideward or rearward drift during the maneuver to reduce the possibility of dynamic rollover or other damage to the helicopter. It is best to debrief the student after each maneuver. Review the maneuvers with the student and point out what was done correctly and what was not. When discussing errors, point out to the student why they happened and what could be done to correct or prevent them. When a student is continuously having difficulty with a particular maneuver, the instructor must find a way to help the student understand what is happening. Helping the student pinpoint exactly what they are doing wrong, and how to help the student learn to avoid these errors is what the instructor should focus on. This permits the student to immediately take corrective action on the next repetition. Take time to talk about the hazards of excessive nose-low takeoffs, exposure to the hazard area of the height/velocity chart, and the dangers of dynamic rollover. Discussing these hazards while performing this maneuver reinforces the need to carefully choose correct flight techniques and profiles. Common student difficulties with autorotation: students have a tendency to look straight down in front of the aircraft while performing an autorotation. By focusing straight down or on the intended touchdown point, the student loses the ability to determine altitudes. Also, students fail to check trim, rotor RPM, and airspeed, and fail to completely close or place the throttle in the ground idle or override position. Autorotation is overwhelming the first few times students perform it and can almost put them into a frozen state of mind. Rather than looking at all the instruments, flight gauges, and directing what flight path the helicopter should be going, they become fixated with the ground and focus only on that. Once the autorotation has been initiated, immediately have the student verbally call out what they should be looking at. For example, have the student say rotors are at 100%, NG is stabilized, airspeed is at 60 knots and the aircraft is in trim. At first, the student is just rehearsing aloud, but after doing more and more autorotations and training them to look at the instruments, gauges, and attitude of the helicopter each time with verbal cues help them remain focused on what is important, landing the helicopter safely. Emergency situations for discussion only. There are a few situations unique to helicopter operations that must be understood if they are to be avoided. Some of these emergencies may only be discussed, not demonstrated, because demonstration would probably result in damage to the helicopter. They are included here to remind the instructor. To make sure the student is able to discuss the problems and how they can be avoided. Vortex ring state, settling with power. Note, vortex ring state, settling with power, is not a discussion-only maneuver in a single rotor helicopter. It can safely be introduced and practiced at altitudes allowing distance to recover. However, settling with power should not be practiced in twin-rotor helicopters due to excessive roll or pitch rates that occur when one rotor is in the vortex ring state and the other is in relatively more stable air. Coaxial and intermeshing main rotor system helicopters should be safe for settling with power practices. Ensure the student understands that settling with power can occur as a result of attempting to descend at an excessively low airspeed in a downwind condition, or by attempting to hover OGA at a weight and density altitude greater than the helicopter's performance allows. Figure 12.3, as is always the case, using a scenario that the student finds applicable to his or her future helicopter career is most beneficial. An ideal scenario type discussion for this can be a confined area approach, in which the winds were incorrectly judged, resulting in a downwind approach, or a job-specific OGA hover type maneuver, long line, filming for news crews, search and rescue hoist operations, external load hookup/release, etc., that puts the helicopter in the required settling with power profile. While common thought is to lower the collective and fly out of the downwash, this may not be the best option due to lower altitudes or obstacles. Through discussion of aerodynamic theory, an option of laterally exiting the disturbed air can be the best option available. In a counter-rotating system, lateral flight to the right often results in the quickest exit from the airflow and affords the pilot the best view of the exit route. The lateral travel is enhanced by the thrust from the tail rotor and introduces turbulent free air sooner to the tail rotor than any other direction. Adding collective while the helicopter is descending vertically only aggravates the situation. Settling with power can occur only if the rotor is powered. A demonstration of settling with power may be required of the applicant for a commercial helicopter rating. The private pilot applicant may be required only to discuss recognition and avoidance, but should have a demonstration of settling with power to understand its effects better. The demonstration should begin at an altitude high enough above the ground to allow room for safe recovery. Entry into the condition can be made from the events as described in the scenario, if acceptable. Another set of circumstances causing entry into the vortex ring state is a decelerating airspeed descent, such as that experienced with a high, steep, downwind approach. This can be used to show the student a probable or likely result of poor or rushed planning. The student should be reminded that settling with power always requires three conditions to occur. 1. Rate of descent greater than 300 fpm. 2. Airspeed less than 10 knots in any direction. 3. More than 20% of engine power applied to the rotor system. By taking away any one of the three conditions, settling with power should not occur. Therefore, the instructor can remind the student to keep the descent slow and less than 300 fpm, keep the helicopter moving into the wind, which normally maintains good airflow at the 10 knot or higher value, and, if altitude allows, reduce the collective to reduce power entering the rotor system. In most instances, a lateral maneuver produces the quickest exit from the disturbed column of air. When simulating an attempt to hover OGA, the airspeed is gradually slowed and power is added to maintain altitude. Care must be taken to avoid any rearward speed. If the helicopter can hover OGA, it may be necessary to reduce power to begin settling, then add power to increase rotor downwash. As soon as the effects of settling with power are noticeable, recovery should be initiated. The noticeable effects are vibration, reduced control effectiveness, and a high rate of descent. Recovery is accomplished by either laterally exiting the disturbed wind or, if altitude allows, reducing collective and lowering the nose to increase forward speed. This moves a helicopter out of its downwash and into translational lift. When the helicopter is clear of the disturbed air, or downwash, confirm a forward speed indication and initiate a climb to regain the lost altitude. Retreating blade stall. The student must understand the limits of high speed in the helicopter and the reasons for imposing them. While structural and airframe design limit helicopter airspeed, the most frequently referenced aerodynamic limitation to helicopter airspeed is retreating blade stall. The symptoms of retreating blade stall are main rotor vibrations, nose pitch up, and a rolling tendency, usually to the left in a helicopter with a counterclockwise main rotor blade rotation. High gross weight maneuvering, and turbulence all tend to aggravate the retreating blade stall condition. Retreating blade stall normally cannot be demonstrated without exceeding the never exceed speed, VNE, or maneuvering limits of the helicopter. However, the student must be able to explain that the cause of retreating blade stall is excessive forward speed for the existing circumstances. The manufacturer's recommended VNE provides protection for normal situations. If the helicopter is heavily loaded and then flown into turbulence at or near VNE, or if it is maneuvered abruptly, retreating blade stall can occur. Ensure the student becomes familiar with the procedure, lower the collective, increase RPM, if possible, and reduce speed, for recovery from retreating blade. The instructor should advise the student that retreating blade stall is only one of many factors that produce the limiting VNE in coaxial and close tandem rotor systems, such as the Command K-MAX. VNE may not be characterized as retreating blade stall due to the counter-rotating blade system. This design may mask the huge stresses on the rotor system until the stresses overcome the structure. The instructor should ensure the student abides by all limitations. When corrective action is introduced at the first vibration indicating retreating blade stall, there should be very little effect. If the blade stall is allowed to progress to the point the helicopter pitches up and rolls, trying to stop the pitch and roll with cyclic inputs only aggravates the situation. Allowing a helicopter to pitch up reduces speed and alleviates the blade stall condition. Roll control is then effective. The best way to prevent students from encountering retreating blade stall is to instill in them the practice of flying at air speeds below VNE. The margin should be increased if turbulence is encountered. Emphasize to the student that retreating blade stall can be avoided by adhering to the VNE. The decrease in VNE speed with increasing density altitude must also be explained thoroughly. Ground resonance. Ground resonance is a hazard associated with an articulated rotor system. Have the student explain which types of rotor systems are susceptible to ground resonance, the factors that tend to cause it, and the means to avoid it or recover from it if it occurs. The student must understand that if the helicopter is allowed to touch down in a manner that creates a jolt or bounce to the airframe, ground resonance can occur. Improperly serviced landing gear struts in some helicopters can aggravate the tendency to oscillate and contribute to ground resonance. This contact with the ground sends vibrations through the aircraft to the rotor system, causing an imbalance and center of gravity shift in the rotor system. The imbalanced rotor system energy is transferred, in the form of a rhythmic back and forth vibration, normally a lateral, or side-to-side motion, from the surface to the rotor system. Although the frequency of this vibration remains constant, the strength of the vibration is amplified until an uncontrollable oscillation develops. Figure 12.4. Since the skids or landing gear wheels contacting the ground cause the rotor to become unbalanced, the obvious means of fixing the situation is to lift the helicopter free of the ground and allow the blades to assume a balanced condition. If RPM is too low for flight, the next best corrective action is to lower the collective to place the blades in low pitch and reduce power plant to idle or cutoff. The vibration increases in severity only if there is power applied to the system. Simply lowering the collective is not sufficient to stop the destruction. Power must be removed. Dynamic rollover is another potentially hazardous situation peculiar to helicopter operation. The student should be able to explain that, for dynamic rollover to occur, some factor must first cause a helicopter to roll and pivot around the skid or landing gear wheel, until its critical rollover angle is reached. Beyond this point, main rotor thrust contributes to the roll and recovery becomes impossible, regardless of any cyclic corrections made. Tell the student that dynamic rollover can occur on a flat surface and most often does due to obstructions such as tie-downs, hot asphalt, and frozen or deep mud. Once the helicopter reaches an angle such that the cyclic cannot keep the rotor system level with the horizon, it is subject to uncontrollable rolling. It is this horizontal thrust component that makes this effect dynamic. Helicopters tend to be top-heavy and easily disturbed in the vertical mode. All of the heavy components, such as engines, transmissions, drive shafts and bearing mounts, tail rotor gearbox, rotor head, swash plates, and blades are mounted high in the airframe in most helicopters. This contributes to a very delicate balance above what can be relatively narrow landing gear. The only possible recovery action is to lower the collective. If the static balance point has not been passed and the roll rate is low, the helicopter might land back roughly on its landing gear. An easy but dramatic demonstration of dynamic rollover can be illustrated by having the student stand straight with his or her feet shoulder width apart and then gradually lean to the side until his or her body extends past his or her center of gravity. At this point, the student will lose balance and will be unable to straighten up. This exercise demonstrates to the student that once the center of gravity of the human body extends too far in any direction, the person topples. The same principle holds true for the helicopter. Point out the factors that influence dynamic rollover to include a skid or landing gear wheel in contact with the landing surface, pedal inputs, lateral loading, asymmetrical loading, crosswind condition, and a high roll rate. Explain that smooth and moderate control inputs are most effective in preventing dynamic rollover as it reduces the rate at which lift/thrust is introduced. Thorough pre-flights ensure the landing gear is fully free. Prudent control movements slowly lift the helicopter off the surface or land without any lateral motion. The rising of one side of the helicopter for compensation for the translating effect should be expected and countered. More or less tilt than normal or usual is reason enough to stop the motion and check for control response. If in doubt, set the helicopter back down and double check for obstructions and skids stuck in hot asphalt, tie down chains or ropes over skids or gear points, etc. While landing the helicopter, the pilot should feel for any sliding or sinking motions, signaling an unsafe landing surface. If such a surface is encountered, descent must be stopped by increasing collective. If after coming to a level attitude, no further attempts should be made to touch down, the helicopter should be repositioned to a different area for another landing attempt. Low G conditions and mast bumping. A student pilot must understand the potentially hazardous implications of intentionally or inadvertently performing low G maneuvers. Too often, students study topics but fail to correlate their impact on the aircraft. Low G maneuvers and the resulting consequences of mast bumping must be thoroughly addressed. Explain to the student that abruptly pushing the cyclic control forward from either straight and level flight or after a climb can put the helicopter into a low G, weightless, flight condition, with catastrophic results. The student must be reminded that the semi-rigid rotor system suspends the airframe below the rotor. Therefore, in normal flight, the helicopter is using the pull of gravity for a normal airframe/rotor relationship or normal load on the rotor system. In a low G maneuver, with the helicopter in an excessively nose-low or tilted attitude, gravity is no longer pulling the airframe down, and the feeling of weightlessness is experienced. With negligible gravitational pull between the rotor and airframe, any cyclic control input tends to fly the rotor disc over. The airframe does not respond, resulting in mast bumping. Ensure the student understands what is happening and that improper corrective action can lead to mast bumping or may allow a blade to contact the airframe. Figure 12.5. Since a low G condition could have disastrous results, it cannot be demonstrated, but the student must learn the correct response. The other part of the low G effect is the thrust of the tail rotor being above the center of gravity. This is often the initial cause of the fuselage to roll. Stress that abrupt movement of the cyclic and collective should be avoided, but if the student gets into a low G condition, be sure to describe the feeling of weightlessness and an uncontrolled roll to the right. He or she should immediately and smoothly apply aft cyclic. Warn the student against trying to correct the rolling action with lateral cyclic. Explain that by applying aft cyclic, lift is redirected to counteract weight and gravity restores the balance of forces. This in turn requires anti-torque, so the tail rotor forces then become balanced as well. Unless the collective is lowered, the thrust never changes. Only the direction of the rotor system thrust and lift is affected. Prevention is the only proper cure for the hazard. Since the best way to prevent low G conditions is to avoid the conditions in which they might occur, suggest the student avoid turbulence as much as possible, since this type of weather induces low G conditions. If the student encounters turbulence, advise him or her to slow forward airspeed and make small control inputs. If turbulence becomes excessive, explain that a precautionary landing should be considered. To help prevent turbulence-induced inputs, demonstrate how to properly support the cyclic arm by bracing it against the leg. Low rotor RPM. Although rotor RPM and airspeed are repeatedly emphasized during training, it is important for the student to understand not only that there are limits to both, but also why those limits have been specifically defined. Ensure the student understands and can explain that the limits for powered operation are dictated by the operating limits of the engine. At low RPM, the engine cannot develop full power, and the high limit is imposed by engine structural limits. Also, point out that if the engine and main rotor RPM are allowed to get too low, tail rotor RPM is also greatly reduced. This situation could lead to an inability to keep the helicopter from turning. At the low limit on the rotor tachometer, the rotor may not produce enough lift to sustain level flight. The high limit of rotor RPM is imposed to protect the structural integrity of the rotor and drive components. Blade stall. Impress on the student that low rotor RPM can also lead to blade stall. If the rotor RPM decays to the point at which all the rotor blades stall, the result is usually fatal, especially when it occurs at altitude. In addition to the main rotor blades stalling, if centrifugal force is decreased too much, there is not sufficient force to keep the blades horizontal. Explain that, even at normal operating RPM, the blades cone upward when producing lift. If the required lift remains high coupled with high angles of attack, the blades bend upward further until there is no recovery. The danger of low rotor RPM and blade stall is greatest in small helicopters with low blade inertia. Explain to the student that a pilot can create the situation in a number of ways, such as simply rolling the throttle the wrong way, or pulling more collective pitch than power available, or when operating at high density altitude. Point out to the student that when the rotor RPM drops, the blades tend to maintain the same amount of lift by increasing pitch. As the pitch increases, drag increases, which requires more power to keep the blades turning at the proper RPM. When power is no longer available to maintain RPM, and therefore lift, the helicopter begins to descend. This changes the relative wind and further increases the angle of attack. At some point, the blades stall unless RPM is restored. If all blades stall, it is almost impossible to get smoother air flowing across the blades. To make matters worse, the main rotor RPM to tail rotor RPM ratio is 1:6. Therefore, a 1% reduction in main rotor RPM can also result in a 6% reduction in tail rotor RPM, which corresponds directly to a loss of anti-torque thrust available and loss of yaw control. Stress that any time the rotor RPM falls below the RPM limits while power is still available, the student should simultaneously add throttle and lower the collective. If in forward flight, gently applying aft cyclic loads up the system and helps increase rotor RPM. If there is no power available, immediately lower the collective and apply aft cyclic. Recovery from low rotor RPM before the student is allowed to solo. The techniques for recovery from low rotor RPM in both a hover and in flight must be practiced. This low rotor training should not exceed any limitations. The instructor should not place undue stress on the dynamic parts of the helicopter, as letting the RPM drop too low can result in excessive blade bending, internal engine stress, including localized overheating not monitored by a gauge or sensor, and blade stop pounding. While in a hover, rotor RPM is reduced until the throttle alone will not increase the RPM. The student should then take the controls and attempt to recover RPM by lowering the collective just enough to allow the helicopter to settle gently toward the ground while increasing the throttle. The objective is to regain RPM without allowing the helicopter to touch down. To prevent touchdown, the collective should be raised slightly to stop the rate of descent. Practicing this maneuver graphically demonstrates to the student that if rotor speed is lost and the helicopter begins to settle, collective pitch alone should not be increased in an attempt to maintain altitude. While in flight, RPM may be regained by lowering the collective slightly and increasing the RPM. Aft cyclic while lowering the collective may also help increase rotor RPM, but is usually not required unless the RPM is critically low. Under certain conditions of high weight, high temperature, or high density altitude, a situation might exist in which the RPM is low even though maximum throttle is being used. This is usually the result of the main rotor blades having an angle of attack that creates so much drag that engine power is not sufficient to maintain or attain normal operating RPM. In a low RPM situation, the lifting power of the main rotor blades can be greatly diminished. Therefore, as soon as a low RPM condition is detected, immediately apply additional throttle, if available, while lowering the collective. This reduces main rotor pitch and drag. Under training conditions, make sure the skids or landing gear wheels do not contact the ground. In an actual situation in which the engine does not have sufficient power to accelerate the rotor, smoothly lower the helicopter to the ground, if conditions permit. Once on the ground, the collective can be lowered a little more to regain RPM. Do not try to maintain a hover by raising the collective when the RPM is too low and the throttle is wide open. As the helicopter begins to settle, smoothly raise the collective to stop the descent. At hovering altitude, this procedure might need to be repeated several times to regain normal operating RPM. This technique is called milking the collective. When operating at altitude, the collective may need to be lowered only once to regain rotor speed. The amount collective can be lowered depends on altitude. Since the tail rotor is geared to the main rotor, low main rotor RPM may prevent the tail rotor from producing enough thrust to maintain directional control. If pedal control is lost and the altitude is low enough that a landing can be accomplished before the turning rate increases dangerously, slowly decrease collective pitch, maintain a level altitude with cyclic control, and land. As instructors, we are aware that in most modern helicopters low or inadequate rotor RPM is an indicator of probable overloading or engine performance problems. Show the student that increased awareness to higher density altitudes is critical. Have the student determine the density altitude at the time this maneuver is performed and note to the student that recoveries at higher altitudes may not be possible. Common student difficulties as the helicopter begins to settle. Students may have a tendency to increase collective pitch to stop the descent. Remember, students often fail to correlate the requirement to reduce collective pitch and increase throttle because previous training emphasized reducing throttle when lowering collective. Brownout/whiteout. Brownout and whiteout are two more helicopter hazards that cannot be demonstrated, but should be discussed with the student. Stress that the helicopter's capability of landing in many conditions make it susceptible to visual obscuration when flying over ground material that can be blown up into the rotors during hover flight at low altitude. Differentiate between the brownout caused by dust and sand and the whiteout experienced in snow conditions. If during normal training sessions, seasonal conditions warrant the need to encounter such conditions, use the time to discuss the proper actions, taking care not to expose the student to an unfamiliar environment. Most often, an approach to the ground will suffice to compensate for these conditions. It should be noted that brownout conditions occur to varying degrees for a given landing zone depending on the aircraft in use, single versus tandem rotor, its configuration, weight, tactics being employed, rapidity of approach and landing, accompanying aircraft, time on deck, etc., and environmental conditions, humidity and/or rain, day versus night, and temperature and density altitude. In general, explain that helicopters tend to begin to experience brownout during an angled, no-hover approach to landing at approximately 1 to 2 rotor diameters above ground level, 50 to 150 feet, with the most serious conditions being experienced at approximately 50 feet and below. As the aircraft slows, the thrust vector of the main rotor disc becomes more vertical, as the aircraft pitches its nose up to decelerate, and the thrust becomes greater as power is added to sustain a hover, or near-hover condition prior to landing. Also, the rotor thrust tends to circulate down, out, then back up and down again through the rotor disc just prior to touchdown. All of these conditions combine just prior to landing, the most critical time for the pilot to eliminate lateral drift. With the helicopter engulfed in the cloud of a suspended particulate material, the pilot loses outside reference and horizon cues. The instructor should stress that the loss of pilot visual reference to a fixed point inevitably causes some degree of unintended pilot or aircraft-induced drift away from the intended line of approach and landing. Discuss how, given the top-heavy nature of most helicopters and the aerodynamics of their rotor discs, landing with lateral drift of any kind can cause the aircraft to be damaged, or to roll over, particularly if combined with a pivot point, such as a rock or rut, upon touchdown. Emphasize the importance of avoiding sideways motion, which can lead to dynamic roll. While the majority of mishaps related to brownout conditions occur during landings, advise the student that a helicopter takeoff may also cause brownout due to rotor wash. Ask the student to explain why it is less problematic during takeoff. The student should explain that the aircraft is accelerating away from the dust, and lateral drift is less of a safety factor, except for obstructions in close proximity to the line of departure. The pilot is able to set a power and nose attitude and fly the aircraft safely out of a zone, and not be overly concerned with induced drift due to restricted visibility. A maximum performance takeoff should be used when taking off from a possible brownout/whiteout condition to ensure the quickest exit possible. If the surface is sand or snow covered, planning for an approach to the surface and being slightly faster than normal should help the pilot avoid a brown or whiteout. Likewise, the takeoff in a possible white or brownout condition should be from the surface and not from a hover in order to exit the condition before the horizon is completely obscured. Highlight the need to first check the helicopter for clearance from the surface by bringing it light on the skids or skis to ensure power is good, controls are normal, and the landing gear is free, then reducing power to allow the air to clear before the actual takeoff. The standard 40-knot takeoff attitude is very important to heed to stay ahead of the majority of the cloud dust/snow cloud that is generated by the rotor system and maximum power to climb out of the surface obscuration as soon as possible. Instructors should note the experience level of the students being flown. Do not use instrument flight terms with students who have yet to conduct instrument flight training. System or equipment malfunctions. Anti-torque system failure. Note, many helicopters have anti-torque failure procedures that can be safely practiced, and will most likely terminate the landing with some sort of run-on landing. An anti-torque failure can occur in several different forms. Impress upon the student the necessity to become familiar with each type of failure, its effects on flight, and the manufacturer's recommended procedure for coping with the malfunction. A discussion of some of the types of malfunctions, as well as probable effects and corrective actions, should be included in any training syllabus. The instructor should also include discussion on the effects of structural design and components. The vertical stabilator, for example, provides a streamlining or trim effect under certain conditions and airspeeds. At what speeds will the vertical fin be most effective, and does that correlate to touchdown airspeed for the respective RFM procedure? An instructor's role is greater than regurgitating already printed information. Go beyond the print and incorporate aircraft specifics and procedures to probable conditions that will help the student obtain a higher level of understanding. Complete loss of tail rotor thrust. Ensure the student understands the complete loss of tail rotor thrust involves a break in the drive system, and pedal input will have no effect on helicopter trim. The tail rotor is providing no thrust to compensate for torque. Fixed pitch settings. Explain to the student that a fixed pitch setting is dependent upon the amount of power applied at the time of the malfunction. If the failure occurs at a reduced power setting, low torque, the helicopter's nose will turn when power is applied. When the failure occurs at an increased power setting, high torque, the nose of the helicopter will turn when power is reduced. Emphasize the use of the manufacturer's recommended procedures for coping with either situation. Loss of tail rotor components. Make the student aware that if the loss of tail rotor components occurs, he or she will also experience a shift in the center of gravity. The student should understand that the severity of the situation is dependent upon the amount of weight lost. Impress upon the student that if a major failure allows something like the drive to begin whipping around, it could destroy the entire tail boom. Extended flight is not recommended after a failure of any kind. The helicopter can be repaired at a remote landing area much more quickly and at a much lower cost than rebuilding the helicopter after a crash landing 3 miles closer to the base of operations. If something on a helicopter fails, follow the RFM procedures. If there is any suspicion of a component failure, safely land as soon as possible. Unanticipated yaw/loss of tail rotor effectiveness, LTE. Loss of tail rotor effectiveness, LTE or unanticipated yaw, is not related to equipment malfunction, but rather is a result of the tail rotor not providing the adequate thrust required to maintain directional control. LTE may occur at airspeeds less than 30 knots and can be caused by a number of factors, including main rotor disc interference, weathercock stability, and tail rotor vortex ring state. It also depends upon wind direction and speed, altitude, and helicopter design. Thus, LTE offers a number of opportunities for the instructor to discuss the principles of aerodynamics and the physics involved in helicopter flight while reviewing a helicopter hazard. To help reduce the onset of LTE, make sure the student understands the limitations of the training helicopter and those circumstances under which LTE is most likely to occur. Additionally, discuss recovery procedures. Forward flight into the wind is best, but it must be in an obstacle-free direction. Not downwind, and the effects of altitude and terrain on the recovery procedure. Main drive shaft failure. Failure of the main drive shaft causes an immediate increase in engine RPM and a decrease in rotor RPM. Explain to the student that an auto rotation is necessary to maintain rotor RPM. Engine RPM should be kept within normal limits to provide power to the tail rotor for directional control if necessary for that helicopter. If the drive system is like that of a Robinson 44, then the engine should be shut down to minimize damage and heat sources. If the main drive shaft of a BH-206 failed, then the engine would be necessary to power the tail rotor for landing from an autorotation. Until the drive shaft separates from a turning drive, it generates a lot of noise and can cause much damage to structures. The pilot may be told to ignore the noise, auto-rotate with the rotor tachometer in the green range, and execute an autorotative landing. Once safely on the ground, perform an emergency engine shutdown and kill all electrical circuits in accordance with the RFM. Hydraulic failure. Explain to the student that the effect of hydraulic failure on the control system in a helicopter depends on the model. Since the hydraulic system is used to overcome high control forces, point out to the student that the first sign of a hydraulic failure is generally a need for more force to control helicopter movement. In those helicopters in which control forces are so high they cannot be moved without hydraulic assistance, 2 or more independent hydraulic systems may be installed. Have the student consult the RFM for the helicopter being flown and then discuss the corrective actions required. Instructors must be most diligent when conducting hydraulic failure training. Some accidents have occurred due to instructors improperly or erroneously following procedures. Discuss with the student the events that will occur before practicing any emergency training. Always have complete understanding, as a crew, of what steps are taken and in what sequence. In helicopters equipped with dual hydraulic systems, the instructor should ensure the student understands the purpose of the backup system, which is to get the helicopter on the surface and not continue the flight. The student should be taught the common parts of the systems, such as a common reservoir or drive pad, and how one failure can lead to failure of the other system. The student must realize there is complete lack of control if the remaining system fails. Governor failure. Many training helicopters and all turbine-powered helicopters are equipped with engine governors. It is valuable training for the student to learn how to manually control the throttle in the event of a governor failure. In some helicopters, the governor can be safely turned off for training purposes. Consult the RFM for correct procedures and techniques. Multi-engine operations with one engine and operative helicopters with 2 engines are rarely found in the training fleet. However, instructors may transition helicopter pilots into these more advanced aircraft. The advantages of having 2 engines are obvious, not only in the redundancy of the engines but also in the power available when both are operating. Students should understand that, in the event of an engine failure, there is still one engine operating and the helicopter is still capable of flight although performance is diminished. The RFM outlines single-engine operations and capabilities for multi-engine helicopters. While unlikely, dual-engine failure is possible and has occurred. Circumstances such as icing, fuel system problems, contamination, or drivetrain failure are just a few examples that may lead to loss of powered flight in multi-engine helicopters. When conducting multi-engine transitions, training one engine in operative emergency flight consumes the bulk of training hours. However, ensure adequate time is allocated to loss of powered flight in dual-engine aircraft. Emergency equipment and survival gear. Ensure the student is familiar with the location and operation of all emergency equipment and survival gear installed or carried in the helicopter. Figure 12.6 shows an example of a typical survival gear and emergency equipment list for a wooded or densely forested location. Students should also be shown sample lists of survival gear for all weather extremes, such as Alaska and Arizona requirements. In a survival situation you can never have too much equipment. Students should receive instruction on and be familiar with the function of emergency releases of all doors, hatches, and windows, as well as operation of all items contained in the list. Discuss emergency egress and basic survival requirements for the locale and time of year. While the intent of this chapter is to discuss instructional points for emergency procedures, it cannot begin to address all emergency equipment and survival gear required for the many different geographical locations and aircraft-specific procedures that instructors may be faced with while conducting training. Therefore, it is important that instructors discuss emergency equipment and survival gear unique to the geographical location and installed on the training helicopter being flown. Also, discuss the requirements of Title 14 of the Code of Federal Regulations, 14 CFR, that apply to the equipment carried on board for the type and area of operation. For instance, 14 CFR Part 91, Section 91.205b, 12, states, for VFR flight during the day, the following instruments and equipment are required. If the aircraft is operated for higher over water and beyond power-off gliding distance from shore, approved flotation gear readily available to each occupant and, unless the aircraft is operating under Part 121 of this subchapter, at least one pyrotechnic signaling device. As used in this section, Shore means that area of the land adjacent to the water which is above the high water mark and excludes land areas which are intermittently underwater. For example, if you're located near a large body of water, expand beyond the required syllabus to discuss what unique characteristics and limitations are present when flotation devices are installed. What impact could they have upon exiting the helicopter? Talk about the emergency procedure required for ditching in water. Discuss when to remove the doors in situations of power off, auto rotations, or power on ditching. When forced to land in water, taking the doors off is critical. However, if the helicopter is in an auto-rotational descent, removing the doors in descent may cause greater problems. If underpowered flight and forced to ditch, with little fuel remaining, jettisoning the doors and then hovering a safe distance away to enter the water is the best option. It is important to discuss the danger of turning rotor blades to those exiting the helicopter and to discuss the best manner to exit. Again, tailor this topic to the equipment and gear installed and used in the training helicopter. This discussion can be quite in-depth and should be based on local procedures, as well as the knowledge of more experienced pilots in the flight area. Scenario-based training. Once the student has mastered engine failure in the hover emergency procedures, this emergency can be incorporated into any scenario by the instructor giving a verbal warning at the appropriate time to indicate the engine has failed. For an instructor, the initial focus of emergency training is to have the student correctly analyze the malfunction and properly perform the corrective action. This is often accomplished with one specific emergency procedure being taught as the center of attention. But how do we know if the student will be able to perform this action if it actually occurs? An instructor should never let the student exceed aircraft limits or the instructor's ability to recover the helicopter. One way to check the student's proficiency and confidence is to build emergency training into a routine flight scenario. Give the student the task of planning and executing a flight to a nearby airport. The instructor will have a predetermined series of simulated emergencies to be given at different segments of the flight. This allows the instructor to plan ahead to ensure the specific procedure to be performed will be in an adequate or approved emergency procedure training environment. For example, one task to be evaluated is anti-torque failure. Prior to entering the nearby airport's traffic pattern, the instructor gives the student a verbal description of anti-torque controllability issues and fixes the pedals. Another example would be to advise the student that the oil pressure is low or the engine temperature is too high. The instructor could announce that the engine is running rough or is cutting out. Simply saying engine failure is counterproductive because the student must learn the signs of an engine failure and not be trained to wait for cues from the instructor. The whole intent of the training is for the pilot to be fully trained and self-sufficient in single-pilot helicopters. At this point, allow the student to work through the situation and take the appropriate actions. If appropriate actions are proficiently executed, the student's confidence level rises and the instructor also feels secure in the student's abilities. Instructor tips: by using simulation or flight training programs, the student experiences the virtual reality of various helicopter hazards, especially ones that cannot be demonstrated due to possible structural damage to the aircraft. Refer to Figure 12.7 for a general lesson plan to be used to help outline training. Chapter summary: this chapter addressed various emergency procedures and provided the instructor with some topics for discussion with the student. Emergencies were discussed in general terms. This chapter is not intended to replace the procedures recommended by the manufacturer in the RFM.